If you're looking to improve the stability of your workflow, the Process Behaviour Chart, or PBC, is the perfect diagnostic tool. Systems are inherently variable, and your first instinct should not be to act on every fluctuation, but instead accept that noise from the natural variation of your process and learn how to identify true signals of the abnormal. With statistical backing, the PBC can tell you when to take action, and more importantly, when to leave your process alone. A process behaviour chart is actually made up of two charts which are interdependent on each other. Located on the top half is the individuals chart, or X chart. It plots the cycle times of each work item in chronological order. It is basically a cycle time run chart. On the horizontal axis, it displays the sequence of the completed items, and on the vertical axis, it shows the cycle time in days. On the bottom half, you have the moving range chart, or MR chart. This plots the difference between each item's cycle time. On the horizontal axis, it also displays the sequence of the completed items. But on the vertical axis, it shows the range, in days, between consecutive cycle times. Together, these two charts, commonly referred to as an XMR chart, act like a combined speedometer and engine check for your process. The speedometer, X chart, tells you the current speed, cycle time, but the engine check, MR chart, alerts you when the engine's internal function is inconsistent or needs immediate intervention. The process signals and basis lines used to diagnose your process stability are calculated from the MR chart. This ensures that your analysis is grounded in the actual successive movements of your work. They are not based on incorrect assumptions about the data following a normal distribution. As mentioned, the process signals are one of the controls in the PBC used to diagnose stability and identify actionable, exceptional outliers called signals. Large change identifies the only true signals in your data. These are data points that exist outside of the normal range, calculated from the MR chart called your natural process limits. In practice, most users of this chart will find plenty of signals using just the large change process signal. However, you can use the more sensitive process signals to find early indicators of a shift within your data's noise. These should be investigated only within a stable process, meaning no true signals are present, and only when they meet the criteria defined by the basis lines, to avoid wasting time and resources. Basis lines are another feature that aid the identification of process changes, whether big or small, by visualizing calculations from your natural process limits. As mentioned previously, these limits are calculated from the moving range chart. Our first basis line is titled Natural Process Limits, or the 3 sigma line. These are the upper and lower boundaries of the natural variation in your process. These calculated boundaries are like a natural range for your process. If a point falls outside these boundaries, there's a really good chance, over 99%, it represents something exceptional. It means something truly out of the ordinary happened, which requires immediate, focused investigation. You need to find and fix the root cause of that specific event. On the other hand, data points that fall within the NPL are expected. It is simply common cause variation or routine noise, the background hum of a naturally variable process that does not require tampering with. This brings us to our next basis line titled 2 sigma, so called as it is 2/3 of the upper natural process limit. If you notice 2 out of any 3 consecutive points being below the UNPL but above the 2 sigma line, this could indicate that there has been a notable shift in your process, which may require attention in the near future. This shift would be highlighted by the moderate change process signal. Next, we have the 1 sigma line, as it is 1/3 of the UNPL. As before, if you notice 4 out of any 5 consecutive points being below the UNPL, but above the 1 sigma line, this could indicate that there has been a notable, prolonged shift in your process, which may require attention if it were to continue. This shift would be highlighted by the moderate, sustained process signal. Lastly, for this chart, there is the average cycle time. Simply, it is the average of all selected cycle time values. It gives you a sense of the process's center. When you see a minimum of 8 successive values on the same side of the average line, but within the NPLs, this may indicate a coming shift in your cycle time, trending up or down, depending on what side of the average line the values are plotted. This shift would be highlighted by the small, sustained process signal. Now that we know how to separate signals from noise, we can explore the overall stability and variation of your process using the MR chart. By measuring the range of consecutive cycle times, this chart can visualize the piece-to-piece jumpiness or volatility in your process and check if the variation itself is behaving consistently. The last 2 basis lines specifically can aid with identifying this. The penultimate basis line is the upper range limit, or URL, and is the ceiling to the natural variation in your process. Data points above this line are true signals, and just like before, they need to be investigated. Signals can appear on both charts or be unique to one. It's good practice to investigate those that appear on both charts first. The last basis line is the average MR. This is simply the average value of the range between successive cycle time values and is used in calculating all but one basis lines. Understanding the PBC is our first step in the right direction of identifying whether or not we have a stable process. But reading the chart means nothing if we're not looking at the right data. To make sure you are, use the date control located at the bottom of the chart to select and view a specific time period. For example, say your company have recently made systemic changes to your process. To analyze the effects of these changes, you need to select the data that is relevant to your current context. Please note, the main date control will only affect the data that appears on the chart. If you want to calculate your basis lines using a different subsection of data, you need to check the corresponding box and a second date control will appear. Incredibly useful for comparing your old limits to your new context to gauge improvement. The key insights offer a quick and convenient method of visualizing the values associated with the process lines in each chart, especially the final insight, as it clearly identifies true signals. These insights are invaluable if your process is unstable, as it directs where your attention and resources need to be focused. But what happens if there are no true signals and your process appears stable because your performance is consistently bad? The PBC's job is not to judge performance or set targets. Its only job is to diagnose stability. So if the chart shows you a stable process, meaning all the data points are behaving predictably within the calculated limits, even if those limits are wide and the performance is poor, it still tells you something crucial. It tells you that to improve things, you can't just react to individual high points anymore. Those points are a part of the system's current capability. Thus, you need to fundamentally change the system. Maybe that means new tools, better training, clearer policies, removing bottlenecks. The PBC confirms that if your system is stable but slow, management needs to redesign the machine and not just yell at the operators running it. Now that you're familiar with how to navigate the chart, you may wish to gain more granular insights into specific facets of your process stability. Like our other charts, you can filter down the data shown by choosing one or more of the available controls, such as the item filter. This would allow you, for example, to compare the stability of certain work item types, teams, or any other attribute you have loaded in with your dataset. Another control you may wish to utilize are the workflow stages. As this chart deals with cycle time, you need at least 2 workflow stages selected. The top checked stage will signal to start the cycle time clock for a work item when it enters that stage, and the last checked stage will signal to stop the cycle time clock when the item enters. This lets you look at the behavior of your entire process, or just a specific portion of it, and allows you to pinpoint if one portion of your process is less stable than another. So, we get the theory. But how do we put this into practice? What does knowing our process mean for managing expectations? How does the PBC help us deal with stakeholders or customers? As you've seen, The PBC provides us with an objective, empirical voice from the data itself, telling you what it's actually capable of, what you are capable of. This often stands in stark contrast to the demands of stakeholders and the expectations of the customer, because arbitrary desire is not based in the hard truth of your system's reality. Your job is to bring those two voices, the customer's wish and your process's capability, into alignment. Because if they are not in sync, you cannot set reliable expectations or make promises you can keep. Trying to deliver something way out of your capability simply sets everyone up for failure. We hope that this deep dive into the PBC helped with your journey for process stability. It can be a lot to take in, so please feel free to reach out to us via our support portal or by email at support@55degrees.se if you have any questions.